Okay, so I wanted to start off thanking the organisers very much for inviting me to talk at this meeting. The meeting's been wonderful so far. I've really enjoyed all of the talks, and hopefully people will be able to enjoy this talk as well. The conversation throughout all of the previous talks have been fantastic with all of the interesting questions. So please feel free to ask questions as we go along here as well. What I am going to talk about is the equation of state from neutron star post-merger remnants. As Julian mentioned during the introduction, I am a member of LIGO. I am going to talk a little bit about some LIGO results towards the end of the talk, but I also want to concentrate more on sort of multi-messenger observations in general. So the image that I've got up on the screen at the moment is a beautiful schematic that was created by Carl Knox, who's an artist in residence at Swinburne University. And this is going to appear in a review article that my PhD student, Nikhil Saran, and I are writing. I just want to sort of leave this up for a moment because I'm going to talk through this diagram in a lot of detail throughout the talk, and we're going to sort of analyze various parts of it and look both at the theoretical foundations as well as the electromagnetic observations, as well as hopefully some gravitational wave observations in the near future. So I will start by just sort of highlighting this region of the diagram, and this is really what the region of the diagram that we're going to talk about. So you can see on the left, let's start off on the left with two neutron stars. They're depicted in this diagram with a little bit of artistic license. They're depicted as being blue because they're cold. I realize and appreciate that sometimes blue things can be hot, but it's artistic license that allows us to draw blue things being cold over on the left here. And they're inspiraling in, and this is of course the inspiral region, and we've seen gravitational waves from signals like this. In particular with 1708-17. I'm also going to talk a little bit later about 1904-25, just very briefly, but these are two gravitational wave in-spiral mergers that we've observed with LIGO that have been spoken about in this meeting. So luckily I don't need to introduce them all that much to you. I'll just sort of talk about some salient properties related to this topic. Okay, so that's panel A. Panel B is obviously when these two neutron stars merge. We'll talk a little bit about that, but really what I want to focus on throughout this talk is the region that has been highlighted with this red ellipse. So you've got two possibilities. As soon as two neutron stars merge, you can either go through this path straight to C, or you can come down to D. And the difference here is that if you go straight to C, this is what we call prompt collapse. And so prompt collapse to a black hole probably launches a jet, which we see as a gamma ray burst. But in particular, this is pretty much instantaneous that a black hole forms after this merger. Of course, on the other hand, there's a very high probability, and I'm going to quantify what I mean by this soon. There's a very high probability that actually we're going to form a neutron star. And this neutron star is going to be massive. It's going to be really hot. That's why we've depicted it as being red here. It's really hot. If you ask me, things like this can still form jets and launch gamma ray bursts as well, and we've tried to depict that with this image here as well. But this thing is rapidly differentially rotating. It's incredibly hot. If you want to sort of study quantum chromodynamics in really hot, dense nuclear matter, this is sort of the region to do it. And so this is one of the main motivations for talking about this. So there are then many paths that you can go along here, and I'm going to talk about these in detail as well. But you can either then form a black hole on some timescale. So if this is what's called hypermassive, it can collapse reasonably quickly to form a black hole, or it can form a more long-lived neutron star. And then there's this branching pathway again, going from F. It can either form a black hole again, or it can even form an infinitely stable neutron star. So which pathway you take here depends upon two main things. One is what the mass of the object is, and the second is what the maximum mass of neutron stars are. So this is how we try and get at the equation of state, through understanding what that TOV mass is, which has been also discussed a lot through a lot of the talks in this meeting. So if we could either know the TOV mass, or if we could understand what the mass of that remnant object is, then we'd be able to get really at the equation of state. So that's really the focus of a lot of what I'm going to talk about. We're going to talk about observational evidence, and so this is sort of a little bit of content slide for what I'm going to talk about. The bullet points going down the left, we're going to talk about whether you go down each of these pathways, prompt collapse, delayed collapse, stable neutron stars, and their relation to the equation of state, and what we believe the sort of masses of these neutron stars to be. So we're going to start off talking about that, and then we're really going to go into the observational side of this science. And actually, I want to go into short gamma ray bursts before we even touch gravitational waves. So we're not going to talk about gravitational waves until a little bit later, but we're going to start off talking about short gamma ray bursts. And in particular, when I talk about short gamma ray bursts, I'm mainly going to be focusing on X-ray afterglows. Okay, so let's start off. This is now just a slice of that diagram, and asking the question, okay, what is this pathway to get a stable neutron star? And very clearly, if I want this neutron star remnant to be eternally stable, then the mass of the remnant, which I'm just going to call M, has to be less than that Tolman-Oppenheimer-Volkov mass, MTOV. And again, this is just the maximum mass of a non-rotating neutron star that the equation of state allows. So this is a quantity that we don't know. We'd love to know it, and we'll be focusing on that a little bit as we go. So that's sort of the first pathway. If my remnant mass is less than the TOV mass, then I have an infinitely stable neutron star. The next case is a little bit more complicated. Suppose the mass of the neutron star, of the remnant, is greater than the TOV mass, but just by a little bit. And when I say just by a little bit, calculations that have been done for a long time now, going back sort of 20 years, calculations show that this mass can be around about 20% above the TOV mass. And the whole situation that happens there is that I don't just form a remnant, but I form a remnant that actually survives for some period of time. And this is what we call a supramassive neutron star. Now, a supramassive neutron star is one that is supported against collapsing because it has this extra centrifugal support. So the idea is the remnant is rotating so fast that you get this extra term in the pressure, basically that acts like a pressure term, which supports it from collapsing. As that neutron star slows down its rotation, it loses that extra centrifugal support and will eventually collapse to a black hole. What the timescale for that collapse to form a black hole is anywhere from about 10 seconds to around about 10,000 seconds. And if you want to sort of see where that equation comes from, or that timescale comes from, there's a paper that I wrote with Vikram Ravi, who's at Caltech these days, back in 2014, where we derived this number. Now, I'll caution that that number assumes that you know something about the magnetic field. And I'm not going to touch on this too much today, but it assumes what we really do think is sort of a canonical magnetic field strength for objects like this. But so the idea is if I form a supermassive neutron star, so its mass is around anywhere from 1 to 1.2 times the TOV mass, it will survive for anywhere up to about 10,000 seconds. This is an approximate number. It's good to an order of magnitude. It will survive for up to 10,000 seconds before collapsing to a black hole. Okay, what if it's more massive than about 1.2 times the mass of the TOV mass? If it's more than about 1.2 times the TOV mass, but less than around about 1.5 times the TOV mass, and again, that's a very rough number, then this is what we call a hypermassive neutron star. And now, instead of collapsing on a timescale of 10 seconds to 10,000 seconds, this thing's actually going to collapse on a timescale anywhere from about 1 to 100 milliseconds. That's the conventional wisdom, and I'll tell you why I put a question mark there shortly. So the conventional wisdom is an object that forms anywhere from 1.2 to 1.5 times the TOV mass. It is still supported by centrifugal support, so the fact that this is rapidly rotating, but it's more than just rapidly rotating. It's rapidly rotating through differential rotation. And that differential rotation provides even more centrifugal support than just for a supermassive star. So that's when that differential rotation gets quenched, or when the differential rotation ceases, in other words, that's when this thing will collapse to form a black hole. And that's why it collapses to form a black hole on a much faster timescale than a supermassive black hole, than a supermassive neutron star. The timescale that sets this collapse time is believed to be the Alfvén timescale associated with the magnetic field. So the idea is that I form this rapidly rotating neutron star. It really, really quickly winds up a really strong component of the magnetic field, a toroidal component of the magnetic field for anyone who's interested in the dynamics and orientations of or geometries of magnetic fields. And that magnetic field is going to restrict the differential rotation. So as that differential rotation gets quenched, the star loses that extra centrifugal support that it requires, and it collapses to form a black hole. Personally, I don't actually believe that this will be on a 100 millisecond timescale. I think it will actually take a little bit longer than that, but that's sort of a bit more of a contentious viewpoint that I have. So I don't want to talk about that too much in detail. If anyone wants to ask me, we can discuss it. So then moving along to the final case, what happens if it's more than 1.5 times the mass of the TOV mass? It's just going to collapse promptly into a black hole. So it's going to form a black hole almost straight away. And that's, in my view, that's the least interesting scenario here. Of course, if we had observational evidence that a binary neutron star promptly collapsed to form a black hole, then we'd be able to backwards out the TOV mass, right? Because we know that it must have been, the remnant must have been over this approximately 1.5 times the TOV mass, and therefore we could work out what that TOV mass is to some degree of accuracy. So this is still absolutely interesting, but of course there's less observational implications of this scenario. So there are our main four scenarios, and we're going to sort of talk about at least most of these cases in terms of what the observational details are. But I'd like to first start off by saying, well, how likely is any of this? Okay, when I merge two neutron stars, what's the probability that I merge two neutron stars and they form a star that's either going to be supermassive or it's going to be hypermassive, things along those lines? So let's think about that for just a second. What I'm plotting here on the, let's just concentrate on the top left plot. This is the masses in blue. This is the masses of all of the neutron stars that are in double neutron star systems in our galaxy. Okay, so the idea is we've observed, I can never keep up with this number, it's something like 10 or 11 or 12 double neutron star systems in our galaxy. And because they're double neutron star systems, they're orbiting one another, and we can therefore measure the masses of those two neutron stars really well. And so it turns out that the masses of double neutron star systems, which is histogrammed in blue here, is pretty tightly constrained around about 1.35 solar masses, plus or minus 0.1 solar masses. And there's a bunch of papers on this, so I refer you to the papers that are cited on the right. Kazilton 2013, there's a really nice one from Alsing 2018, and there's another one from Nick Farrow, who's an undergrad student at Monash University, who also wrote a really nice paper on this too. So what I've then gone and done is I've just fit a Gaussian-ish distribution through this. This is the black curve. This is my double neutron star mass distribution that I might expect, given what I know about things in the galaxy. Okay. If I then move over to the right-hand plot, I'll get back to the red curve in a second. If I then move over to the right-hand plot, I can see I've calculated the Chert mass for each of those double neutron star systems. And the Chert mass, hopefully you know, is just a weird combination of the individual masses of the neutron stars that we use to observe gravitational waves. And the reason I've done that is just to overlay GW 170817 on this system, on this plot, and that's that green vertical line. So you can see that the Chert mass for 170817 fits absolutely beautifully with the distribution of double neutron star systems that we've observed in our galaxy. So this is all wonderful. We think, or at least this was the sort of state of the art not that long ago, we thought we understood how massive neutron stars are in our galaxy. Oh, sorry, any neutron stars are in double neutron star systems. For extra reference, and we'll come back to this in a little bit, the red histogram on the left-hand plot is the masses of other neutron stars in our galaxy that are not in double neutron star systems. So they're orbiting white dwarfs and things along those lines. Okay, but what I can do is I can take the black distribution here. So this is my predicted or my fit distribution to our double neutron stars that we observe. And then I can say, okay, I can do a calculation. If I merge two neutron stars, I throw off a little bit of mass, but not a lot. I need to conserve baryonic mass rather than rest mass. I can do this calculation. And when I do that, I can predict what the remnant mass of binary neutron star remnants should be. And so this is just an example of that plot. It doesn't vary too much depending on the sort of, assumptions you make. There's some subtle terms in there associated with the equation of state and with relativistic gravity, but we're not going to worry about those details here. This is, to a really good approximation, this is accurate. When you lose mass through tidal interactions, it's on the order of 0.01 or 0.1 mass, solar mass at the absolute most. So it doesn't really come into play here. So what you can see here, this is a remnant mass distribution that we might predict all our remnant neutron star mergers to have. And I'll point you to a paper that I wrote in 2014 where we do this in order to actually measure the equation of state from some systems that I'll talk about in just a second. But what you can see here is, okay, the distribution is centered around 2.4, 2.5 solar masses, but it's, plus or minus about 0.2 solar masses. So as has been discussed previously, we know neutron stars exist above 2 solar masses, or at least around about 2 solar masses. So our maximum TOV mass, or our minimum TOV mass must be at least 2 solar masses. But let's take an example here. And what I'm going to do is I'm going to say, let's use an example where the TOV mass, for the sake of argument, is 2.25 solar masses. What that means is I can draw a vertical line at 2.25 solar masses. Anything to the left of that, if I draw a random binary neutron star merger out of the population, then the fraction of the population to the left of that 2.25 solar masses, that's the fraction of the population that are going to form stable remnants. The region in the blue is that TOV mass multiplied by that 1.2 number that I had on the previous slide. And so anything in blue there is actually going to form a supermassive neutron star. It's going to survive for some tens of seconds, up to 10,000 seconds before collapsing to a black hole. Anything in white, right up above that, is above this sort of 1.2 times the TOV mass. And it's only those ones that are going to form this hypermassive or prompt collapse. And I've sort of clumped them all into one. So what this is then telling me is that anything that's, if I integrate this out, anything in the blue region is going to form a supermassive neutron star, and that's most of them, right? That's most of the stars are going to be, at least in this example, are going to have supermassive remnants. So this is interesting. Even if I was to take, and this is the text box in the bottom right, highlighted in red, even if I take the TOV mass as the most conservative thing that I can think of, which is 2 solar masses, so that it just satisfies our pulsar observations, then I still get a really, really large fraction of remnants are going to be either stable or supermassive, okay? And almost all of the rest are going to be hypermassive, with only a tiny amount promptly collapsing to form a black hole. Okay, so it's worth having all of that in your mind as we're moving forward. Whenever I see 2 neutron stars merge, whether it be through gravitational waves or whether I see a short gamma ray burst, I should always be thinking that actually the likelihood is that something relatively long-lived, and whether that means, up to 100 milliseconds, or whether that even means up to 10,000 seconds, something relatively long-lived is going to survive that merger, okay? So let's start looking at this in a bit more detail. Let's actually flick to observations now. What I'm showing here, and what we're going to do is we're going to start off talking about the case where I have sort of a very, very long-lived neutron star that survives. What I've got here is there's a beautiful paper by Antonia Rollinson from back in 2013, and it really sort of cracked this field wide open as far as I'm concerned. And what I'm showing here are just two plots from that paper. And we're going to talk about a whole set of these observations, for the next few minutes. But if I look at all of these observations, so what I've got is two short gamma ray bursts, 061201 and 090510. You can see the X-ray afterglows that last for up to 10,000 seconds after the merger. So I've got the prompt collapse right on the left, the prompt emission right on the left, and then X-ray afterglow. And what Antonia and colleagues have done, is they've fit a millisecond magnetar model through these curves. And so the X-ray emission here, as far as this black curve goes, comes from the emission of X-rays coming from a spinning down neutron star. So absolutely gorgeous, fits the observations really, really well. And there's a whole sort of whole field of literature on this subsequently. And I'm going to talk about some subset of that. That's half of what the Antonia Rollinson paper is about. The other half is that there's all of these other beautiful observations, for example, 090515, where actually what you see is some X-ray afterglow observed with Swift again, but then all of a sudden that X-ray afterglow just switches off. And it switches off and all of a sudden you've got no more X-rays. And this has been very commonly interpreted in terms of that supermassive model where therefore the neutron star has collapsed into forming a black hole. Okay, so we've taken these observations and there's a couple of papers here. The most notable, I would say, is the one that's led by Nikhil Saran from last year, who, as I mentioned, is my wonderful PhD student. If anyone has postdoc positions, he's on the lookout. You couldn't hire any better, as far as I'm concerned. But so we took two of the GRBs with the sort of the best observations that we have. And this is that 130603b. And for anyone who's playing at home, this was sort of the first GRB that had that we think has a kilonova observation as well. But we'll ignore that for the moment. And 140903a, which has, again, very long-lived observations up to 10 to the 6 seconds. And in fact, what we can do is we can measure the breaking index of this spin down of the neutron star. And so the breaking index, if it was up at 5, it would tell us that this thing's being spun down through gravitational wave emission. The fact that it's down below that and it's down at sort of 2.5 to 3 means that the spin down of this neutron star is consistent with electromagnetic observations. But really the important point, with the spin down is consistent with electromagnetic spin down. So where the spin down is dominated by the magnetic field. But really the point that I want to make here is that what you can do is you can go a step further, and this is what was done Nick did in his 2019 paper. You can actually ask the question, does this data better fit a millisecond magnetar model where the neutron star is spinning down like this, or does it better fit the fiducial sort of forward shock model that we have for gamma ray bursts? And the answer is actually it depends on your prior knowledge of neutron star physics. And for the lack of time, I'm not going to go into this in too much detail, but basically for all intents and purposes, what we're saying here is that yes, these gamma ray bursts are absolutely better fit by neutron stars that spin down, but only if that TOV mass is above 2 solar masses in the case of 140903, and in fact above 2.2 solar masses in the case of 130603. So if we went back and, if we knew what the TOV mass was, we'd be able to say with much, much more certainty whether it is or it isn't the spin down of a neutron star in these systems. But at least for 140903A, we are, beyond confident. We are almost, for all intents and purposes, 100% confident that this is a neutron star spinning down as the post-merger remnant, causing that X-ray emission. Okay, so I'm actually going to skip that slide, and I'm going to talk now about that was the case where we see these X-ray emission, and the X-ray emission doesn't shut off. So the X-ray emission lasts basically as long as we're observing. What about the case where, we talked about supermassive neutron stars where the neutron star perhaps collapses into a black hole? And I showed these two plots from Antonia's paper where the X-ray emission just shuts off, and you can fit this really well and you can work out what that collapse time is, and that collapse time can then again tell you about the equation of state of nuclear matter. what's really, really interesting about this, and we sort of, there was two papers that came out almost quite similar times, one by Fan in 2013 and one by Vikram and I that I've already mentioned in 2014. And what we both pointed out, but we both accounted for this in very different ways, was that when you look at the collapse time of these systems, it doesn't really agree with what you would expect. So they seem to be collapsing a lot earlier or a lot sooner than what you would expect just through, you know, the simplest naive arguments that you can make. Now, a lot of authors then went on to interpret that in a lot of different ways. So, and in fact, there's this beautiful set of literature where some people just say, that's okay. This is because these systems emit a lot of gravitational waves, a lot of energy through gravitational waves. So the spin down is actually faster than you would otherwise naively predict. And when I say naively, exactly what Vikram and I did in 2014, we were naive. We assumed there was no gravitational wave emission extracting energy or angular momentum from these systems. So if you do assume that there's gravitational wave emission, they will spin down a lot quicker. But then there was these other whole series of papers by people like Ang Lee, Marco Drago wrote a handful as well, and all of their collaborators as well, that said, well, hang on, you can actually get this premature collapse of systems like this if it's got nothing to do with gravitational waves, but actually if the star has a completely different moment of inertia to what you might otherwise expect. And if that, why would you have a different moment of inertia? Because the star actually has a completely different equation of state to what we, again, naively expected. In other words, if there are things like deconfined quarks. So people like Ang Lee wrote these really nice papers that said, this might be evidence that gravitational waves, you know, quark matter exists in these stars, and therefore this is the thing that sort of is what's causing these things to collapse. So there's a lot of debate in the literature about this. What we've then gone and done is we've tried to incorporate all of this also with a lot more observations. And again, this is another beautiful paper that Nick wrote and just been published earlier this year, where the title is Gravitational Waves or Deconfined Quarks, What Causes the Premature Collapse of Neutron Stars Born in Short Gamma Ray Bursts. And the whole idea here is there's actually 18 of these gamma ray bursts, and we can quantify in a very statistically rigorous way the probability that these were neutron stars that collapsed or that they weren't. And so we find that there's 18 of these supermassive systems of short GRB remnants. We can marginalize over the unknown redshift. That's all fine. We know how to do that. We include a model that includes, you know, this variable breaking index. So it includes the potential for gravitational wave emission, but it includes as well this unknown equation of state and the capacity for us to believe in you know, deconfined quark equation of state, which would change the spin down, et cetera, et cetera. And we then used hierarchical Bayesian inference to determine these population properties. So that's just a fancy way of saying that instead of looking at individual GRB remnants on their own, we analyze the population as a whole in a really statistically rigorous way. So this is absolutely beautiful, and we were well on our way to publishing this result, and then a spanner got thrown into the works. And so I want to return very quickly to this mass distribution that we were talking about before. What is the mass distribution of binary neutron stars or double neutron star systems? So this was the state of play in sort of 2018, I suppose, after 1708-17. This is the plot I showed earlier. But I'm going to add another line on the right-hand side, because, of course, as Jocelyn mentioned in the previous talk, and Jim Latimer mentioned the other day as well, as LIGO, we observed this new system called GW 1904-25. And 1904-25 really threw a spanner in our works, because we believe it to be a double neutron star system, but a double neutron star system where the chirp mass is over here. It's almost 1.5 solar masses. It's really, really well measured by LIGO. So there's no issue there. You know, the width of that purple line that I've just put on this right-hand plot actually is pretty representative of the uncertainty on the chirp mass. We measure that very well, but it does not agree with the double neutron star mass distributions that we see in our galaxy. So there's a lot of open questions here. a lot of population synthesis. People think that's actually not a surprise. There are always selection effects that you have in radio observations when you're trying to measure double neutron star masses in our galaxy. And short gamma ray bursts and gravitational wave observations have a different set of selection effects. So maybe it's not a surprise, but what it does tell us is that the gamma ray bursts that we're observing, that I was talking about on previous slides, may actually come from very different mass distributions to the naive one that we were originally thinking. So what we've done is we've tried to account for this, and we re-derived our remnant masses in a handful of different ways, but there's a whole lot more uncertainties. And you can argue that maybe there's two populations of neutron star, double neutron star systems. One is the radio population that we see. The other is, for example, consistent with the masses of other neutron stars. They might have formed through different formation channels. There's all of this really interesting astrophysics that I'd love to talk about, but I'm going to exclude from this talk. But what we end up with is, some understanding of, or at least a lack of understanding of, the remnant mass for post-merger remnants. And so there's possibly a second bump. This is what we've done in our paper, but there's no way that, this is the final story on this front, trying to work out what this remnant mass is. Okay, so you can take this regardless. You can take it at face value and you can say, actually, in a statistically rigorous way, what I can do is I can marginalize over my uncertainty. So I can account for my lack of knowledge about that remnant mass. I can include it in my fitting and in my understanding of the statistics. And so this is going back to that previous slide. Instead of just marginalizing over the unknown redshift, now I also need to marginalize over the mass distribution of the progenitors of these double neutron star systems. And it turns out when you do that, you end up, unfortunately, in a situation where you only get very weak constraints on the TOV mass. So this is on the left here. This is a plot of the posterior distribution for the TOV mass that we get when we look at these 18 systems. It's not as good as we would have liked because, it's kind of degenerate with this unknown progenitor mass, and that's a problem. Now, you can sort of take slices through this. For example, if we assume that 1904-25 is not a neutron star merger, then we go back to the old way of understanding mass distributions. And in that case, you get a much better constraint on the TOV mass. And it's somewhere between sort of 2.2, somewhere between 2.0 and 2.4-ish, okay? But, taking into account our unknown progenitor mass distribution, unfortunately, this is the best we can say. But I will say that the more gravitational wave systems we observe, the better a handle we'll get on that mass distribution. And once we understand what that mass distribution is, we'll be able to convert that into a really nice measurement of the TOV mass. And this nice measurement of the TOV mass is completely independent of sort of other measurements that are being made. So it's a complementary way to measure the TOV mass compared to other methods that exist in the literature. I want to say just sort of one more very tantalizing thing about this analysis. I mentioned that what we can include is different equations of state. And it turns out that there's a parameter space in which you can sort of talk about this equation of state, where you get clumps and hadronic stars clump in one region of this equation of state, and I've highlighted this in blue here, and quark equations of state clump in another region. And in doing this kind of analysis, then we can then come up with a posterior distribution in this space. And just for some reference, what this is, these are what we call alpha and beta. They are the way in which a neutron star will support itself from collapse due to that rapid rotation. It turns out that changes whether you have, as a function of the moment of inertia. And so therefore that changes as a function of whether the star is a quark equation of state or a hadronic one. The punchline of all of this is we have what we can only describe as the incredibly weak evidence that quark equations of state are favoured. And so, they're favoured at the 1 sigma level. So they don't even pass an astrophysicist's sniff test. They certainly don't pass a particle physicist's sniff test. But it's worth saying that the more observations we get of systems like this, the more we'll be able to understand this. And I think that this might actually end up being a good discriminator between these two various classes of equations of state, whether you have deconfined quarks or not. So again, that's just very tentative. There's no, I wouldn't call it strong evidence in the least. It really is a 1 sigma result, but I think it's interesting nonetheless, and it's interesting to pursue this method and see if we can do any better. Okay, so I want to pivot now to talking about just this region of this diagram. And so this is this highly dynamic phase. It lasts for maybe 10, maybe 100 milliseconds, maybe a bit longer, but not a lot. It's when the neutron star is really, really hot, anywhere up to sort of 10 to the 10, 10 to the 11 Kelvin. So that sort of equates to on the order of 50 MeV in parts of the star. And it's a really strong emitter of gravitational waves. So this is an opportunity to measure the hot equation of state as opposed to the cold equation of state in frame A here. So during the in-spiral phase, you might measure the cold equation of state, and this is an opportunity to measure the hot equation of state during that post-merger phase. So let's talk about that section. So this is sort of ignoring the gamma ray burst side for a little bit. Yesterday, speaker Jocelyn Reed wrote a beautiful paper way back in 2013, and this is sort of just one of many papers that point out this idea. But the whole idea is that the gravitational wave spectrum that you get from this post-merger remnant is really, really sensitive to the equation of state. Okay, so this is a plot from Jocelyn's paper from back in 2013. What it shows is 4 different equations of state. Some of them are probably ruled out now, but it doesn't matter. It's for schematic purposes, it's wonderful because it shows the 4 different equations of state, which all have sort of different levels of stiffness. And they're just sort of phenomenological equations of state, I believe, but they have very different peak frequencies. So you can see that the 2H equation of state has a peak frequency at sort of 1,700 hertz, give or take. The H equation of state is 2,800 hertz, and so on. So in other words, the peak frequency or the dominant frequency that you get in the post-merger remnant is really sensitive to the stiffness of the equation of state. So that's wonderful. That means basically we can measure the gravitational waves from this post-merger remnant, and we'll have some chance of understanding this hot equation of state. I just want to very briefly mention there's a lot of algorithm development that goes on both within LIGO and without, and here's just a couple of papers that talk about how to detect and characterize these signals and then learn about the equation of state, not just from that peak frequency, but from the entire spectrum. And one of my PhD students, Paul Lasky, with Sudash and Gondra and other people, I've been sort of working on this, as well as the Bayes wave folk, Katerina Chatianu and the like. Okay, but I don't want to sort of harp on about that. I want to get more to the physics, and I put this slide back into my talk after I heard during Jocelyn's talk a little bit of discussion about this. People were asking the question, can you measure phase transitions in the hot equation of state? And I'll point you to a beautiful paper by Andy Bauswine from last year, and he's written another one this year as well on a very similar topic. But the whole idea, and what's shown on the left here, is a plot where if you don't have any deconfined equations of any deconfined quark equations of state, then what you expect is on the horizontal axis here is the measurement of the tidal deformability that you get from the in-spiral phase. And on the vertical axis is this peak gravitational wave frequency. And if there are no deconfined quarks or no phase transitions in your neutron star as a function of temperature, then what you end up with is this gray band where you would say, I measure this lambda parameter, I measure the peak frequency, and almost always the measurement will fall somewhere within this gray band. But then what Andy pointed out in this nice 2019 paper was that actually if there is a phase transition, the peak frequency that I see in the post-merger remnant is going to change, and it's going to be offset from what I would otherwise expect given a tidal deformability. And in fact, the degree to which it's offset depends sensitively on where that phase transition occurs and how strong it is. And so that's what's sort of plotted here. But in answer to some of the questions that were asked during Jocelyn's talk, absolutely, this is one of the best places to try and measure some kind of temperature-dependent phase transition. The difference between the in-spiral and that post-merger remnant should be highly visible if we can get at these gravitational waves. So, okay, it would be remiss to have a talk about this and not mention 1708-17. So 1708-17 has been discussed a lot. It was a binary neutron star merger that happened just at 40 megaparsecs, so incredibly close. We have these beautiful gravitational wave observations. As you know, we measured the mass of this object, we measured the tidal deformability, we did all of that wonderful science. The question becomes, did we measure any gravitational waves from the post-merger? Unfortunately, the answer is no. And in fact, if you look at this plot on the top left, let me just sort of highlight it again. This plot on the top left shows the gravitational wave frequency as a function of time. And actually, you can see that the signal cuts off at around about 400 hertz. That's nothing to do with the signal. That's to do with the noise in the interferometers. So the noise actually in the interferometers is, or the sensitivity is, the instruments are most sensitive around 100 hertz. And by about 400 or 500 hertz, we really are getting a lot less sensitive to gravitational wave signals. So the signal probably merged somewhere up in the kilohertz regime. And so we didn't even see the merger, let alone that post-merger signal, which you expect up in sort of 1 to 2 kilohertz. So what did we see post-merger? Absolutely nothing. We saw no gravitational waves. I was part of these LIGO papers that sort of wrote about trying to find gravitational waves, and so I'm happy to answer questions. I'll just point to the right-hand plot here. All this shows, in a sort of clunky-ish way, is if 1708-17 had happened at a different distance, how close would it have been for us to have had to measure it? And all the different curves are to do with the different pipelines that are used. So you can sort of use that, ignore that. That's a technical issue about how you search for these gravitational waves. But kind of generically, you see that actually 1708-17 would have had to have been about 40 times closer than it was for us to be able to detect anything. Okay, so phrase that another way, because the gravitational wave strain is inversely proportional to the distance, if our detector had been about 40 times more sensitive, we would have had a chance of seeing something. Okay, and that'll be important in a few slides' time. So we didn't see any gravitational waves from the post-merger remnant, but then again, we wouldn't have expected to, so that's okay. You don't expect those gravitational waves to be loud enough, and there's all these theoretical calculations that support that idea. But there's all of this other evidence that points to either short-lived or long-lived neutron stars, and I'll just flick through this very quickly. The color of the kilonova, for example, people have been saying that supports the idea that a neutron star survived for at least many tens of milliseconds. Okay, if that's true, great, but we don't really know because some groups then go and fit the kilonova with long-lived remnants, others with short-lived remnants. Each group says that they fit something and it all works. I'll also say that about 160 days after the merger, there was also a bump in the X-rays. Whether that had to do with some kind of post-merger remnant that survived as well, there's a lot of speculation. All I would say really is that there's a lot of evidence either way. Did a short-lived or a long-lived neutron star survive the collision? We have no idea, I would argue. And anyone who tells you different, I would say, I think they're speculating a little bit too much. The only thing I think we can say for certain is that it didn't form a black hole, straight away. Okay. So that's sort of 1708-17. 25 was a lot further away. It was a lot more massive. We have no idea, but that probably formed a hypermassive neutron star and then collapsed, or even prompt collapse. But again, that's all kind of speculation. We didn't see anything electromagnetically, so we don't have that extra observations. I'm sort of getting the wind up to him, and I want to make sure I take questions. So I just want to talk very briefly about what's next in gravitational wave astronomy, because I think this post-merger remnant stuff is really where there's a lot of interesting and beautiful physics. So what's next in gravitational wave astronomy? Here's a plot of the gravitational wave strain, or in other words, the sensitivity of advanced LIGO as we speak now, or during 03, for example. Advanced LIGO has a design sensitivity, a factor of about 2 beta, so that we're hoping to get to by about 2022-ish, give or take. Then there's this thing called A+, which is funded, which is another factor of a few more sensitive. Okay, but this is not getting to that factor of 40 that we need to be able to detect that post-merger remnant. And then there's this huge gap between Cosmic Explorer and Einstein Telescope, which are these full third-generation telescopes. These are not funded. These are uncharted territory in terms of technology. There's a lot of work going into them. There's a lot of design study money that's being put towards them. They're absolutely fascinating, but really these things are 20 years away. They're 2 decades away. So the question is, what's in between? And so this is where we introduce what we call NEMO. NEMO stands for Neutron Star Extreme Matter Observatory. And this is this red curve, and it's a proposed detector. And sorry, I've got the wrong label on my plot. It says OzHF. It should say NEMO. This is a proposed detector that sacrifices all this low frequency sensitivity. So you see at low frequencies, it really does a very poor job. And in fact, below sort of 100 hertz, it's not sensitive to anything at all. But it is sensitive up at these kilohertz regime to this post-merger signal. And that's the whole idea, is that we want to try and detect post-merger remnants with an instrument like this. So I'm just going to very quickly flash to this plot. This is a plot that, the plot on the right here is the average number of gravitational wave post-merger detections that I expect with NEMO versus what I expect with just A+. Okay, and so if you look at the blue lines, the uncertainty on the vertical axis is the average number of detections per year. The blue line tells me that in the A+ era, I would expect anywhere from one merger remnant to be observable every 10 years to observing one every 100 years. In other words, I'd have to operate these things for anywhere from 10 to 100 years to detect one post-merger remnant. Whereas if you can build NEMO, which is a sort of small-scale instrument, only costs you $100 million, it's a drop in the ocean. If you can build something like that, then you actually get up to that region where you expect a detection anywhere from one every couple of years up to many per year. So it's really taking you into that era of gravitational wave astronomy where you are going to make regular detections of the post-merger remnant, and therefore get all of that, really interesting hot equation of state physics that we were talking about. Just to say that there's a lot of work that's gone into this, and so we do have preliminary designs, and we understand from an instrumentation point of view how you would actually have to get to building a detector like this. Initial costings suggest it would be on the order of $100 to $200 million. Compare that with a budget for Cosmic Explorer, which is upwards of $2 billion, and I would argue that this is worth funding. So if anyone's got a spare $100 million in their back pocket, that would be great. That might not be realistic, but I think it's an interesting idea nonetheless. So I'm going to end it there, and I want to thank the organisers again, and I'll take questions if there's time.
Yeah, thank you, Paul, for a very nice and wonderful talk. There are a few questions, so I'd like to take one by one. So first question is, let me just 1 minute. Yeah, from Harris, which properties of the pre-collapse neutron star are basically depends to form the hot neutron star rather than black hole after 2 neutron star collapse?
Yeah, so thanks for the question, Harris. So it's the most pertinent property of the pre-merger neutron stars are their masses. But on top of that, it's not just the individual masses, but a little bit to do with the mass ratio as well. Because if I have a high mass ratio, so say I have a 1.1 solar mass neutron star merging with a 1.6 solar mass neutron star, then when these two things merge, it's going to throw off more mass than an equal mass merger. So you lose more mass, and that'll affect then what that post-merger mass is and whether it collapses into a black hole. So that's sort of, in terms of I would say that that's the dominant two things is just the progenitor masses and the ratio between those two masses. Obviously, it's then the TOV mass is the most dominant thing, but that's something that is fixed. You know, once you understand the equation of state, then you have a TOV mass, and therefore you're done.
Yeah. The next question is from Unnati. What powers the jet in gamma rays?
Yeah, so I think I saw this question come up, and I think what the question is probably asking is if a long-lived neutron star exists, how do I launch a jet? Okay, and the reason that question comes about is there's a little bit, in some communities, there's a conventional wisdom that you have to collapse to a black hole to then form a Blanford-Genaic jet, right? So you've got an accretion disk around a black hole, the magnetic field gets anchored through the black hole and gets launched out the poles, and then the matter gets stripped off, and that's what launches the jet. There have been many cases of, well, first I would say, we see jets ubiquitously coming off, for example, pulsars. So we know that jets can get launched from isolated neutron stars. So it's never been really obvious to me why you would need to form a black hole in the first place. There's a lot of mechanisms. I think, again, if you just wind up a really strong magnetic field, then you can sort of launch it along that axis again, whether I have a black hole anchoring it or whether I have a neutron star anchoring it. So to me, it becomes then an observational question a little bit. There are, the observations I've pointed to, if we could definitively say that these are neutron stars, they're in the post-merger remnant, and a jet has been launched, then our work here is done, and we need to understand from a theoretical point of view how that happened. Certainly, there are already numerical relativity simulations that do show tentative evidence for this, where there are long-lived neutron stars, and they form really coherent structures in the magnetic field coming out of the poles, which looks like the start of jet formation. But the numerical relativity simulations can't simulate for long enough to really work out if that's, if that's the true mechanism. So, that's a very long-winded answer, but it's a really complicated question as well, and a good one that we should be asking.
Okay. Next question is from Rana. Does viscosity play any role to smoothen the differential rotation?
Yeah, good question. Yes is the answer. So there's a lot of unknowns here, and I'd be really interested to hear from some of the more nuclear astrophysicists and nuclear physicists on this question. But you can have there's two viscosity terms. There's a bulk viscosity and a shear viscosity term that come in. They can be really, the way they scale is really dependent on the temperature. It's the temperature to some high power. So the fact that these neutron stars are so hot means that the ability for the viscosity to quench the differential rotation is a little bit unknown. Most papers and this goes back a number of years now, most papers suggest that the dominant mechanism for quenching the differential rotation should be the magnetic field. But I think I don't think it's a really solved question, because the numerical relativity simulations, they don't treat this viscosity properly. They have numerical viscosity, they have their own problems. So you really need to understand this from a sort of fundamental physics perspective. And I think that's a little bit of an open question. It's a good question. Maybe that's what will speed up the collapse. I don't know, but it's a really good question.
Yeah. So next question from Surendra. He has 4 questions. We'll very quickly go. But first question, that how are the coefficients of MTOV and the intervals are obtained, which you use in your analysis? Are they based on set of inner simulations from observations or some semi-analytical studies?
So I assume that when you talk about the coefficients of MTOV, I think you're probably talking about the collapse of, so whether it's supermassive, so it's the 1.2 times the MTOV mass will form a supermassive star and things like that. So I'm going to answer assuming that's the question. Let me know if that's not right. Those are calculated originally going back a number of years. They were calculated from some sort of quite primitive numerical relativity simulations, and I don't mean that in an insulting way. It's wonderful work. It's just in the early phases of numerical relativity. So they've both been done now through numerical relativity calculations, through quasi-equilibrium calculations, looking for stability points and things along those lines. There are different, especially for the differential rotation, it depends upon your differential rotation law and how you define that differential rotation. There are some recent papers, I think Luciano Rizzola and his group have got some really convoluted differential rotation laws, and they find they can increase that 1.5 times the TOV mass up to a much higher number, for example. Whether that actually occurs in real life or not, I don't think they do, because that's not what we see in numerical relativity simulations of binary neutron star mergers. So I think, the answer to your question specifically, it's a combination of numerical relativity and everything else, and semi-analytic calculations.
Okay, and also, are these lifetimes of HMNS and SMNS, etc., reliable and are compared to any other similar analysis?
Yeah, so I would argue that the lifetime of the hypermassive neutron star is not reliable. And the reason I argue that is because I don't think we understand how magnetic fields quench that differential rotation. I think there's some unknown terms in there. And I shout from the top of hills this belief of mine. I don't think it's been shown rigorously. And if you look at numerical relativity simulations, one of the reasons that they show collapse on certain timescales is because of numerical viscosity, which, nature doesn't have numerical viscosity. So, I think that's an open question. For supermassive neutron stars, it depends on the assumptions. You can throw in a lot of different assumptions into the calculation. For example, how much gravitational wave emission dominates early, whether you have these various types of instabilities. There are, secular bar mode instabilities, how much R modes play a role, all of these other kinds of things. How strong the magnetic field is, what angle the magnetic field has with the rotation axis, all of these things. So are they reliable? No, I don't think they're reliable. Some of my work gets quoted a lot for those numbers, but I would be the first to claim that they're not reliable. But they're an interesting question. And again, that's what we've tried to get at with Nick's most recent paper, Nikhil Sarin's recent 2020 paper, is we've tried to get at it from the observational side. What does the observations tell us? And then can we infer the physics from that?
Okay, so next question is actually forwarded from YouTube Live, Yangao. You talked the critical mass 1.2 MTOV. Do you assume the remnant undergoes uniform rotation?
Yes, so that's exactly how you have to get to this 1.2 limit. So the difference between the hypermassive and the supermassive is that hypermassive can be differentially rotating, but then that 1.2 coefficient, that comes in because you've assumed that the thing is now rigidly rotating or uniformly rotating. So all of those calculations that people have done that tell you that the number is 1.2, they've done that by assuming that the thing is rigidly rotating. I think that's perfectly reasonable, because anything that you do, any kind of viscosity you add into the star, whether it be bulk or shear viscosity, or whether it be magnetic field that quenches all of those are going to act to quench that differential rotation and stop it. So I think that's right.
Okay, the one more question again from because that what kind of US gives MTOV equals to 2.5 solar mass for stability?
I will defer that question to the experts on equations of state and how to construct them from nuclear physics. I see equations of state that do that quite a bit. There are better experts in the room than I on that. So that's a good question. I will note that, before we observed a two solar mass neutron star, nuclear physicists thought that they couldn't create anything greater than 1.7 or 1.8 solar masses. So my perspective, the way I like to do this, I like to consider myself an astrophysicist or an astronomer. So I want the observations to tell me, and I want the nuclear physicists to then feed into that and tell me if it's possible or not. So I'll defer that one to them.
Okay, and one question that from Ritam: will not the amount of mass lost during collision depend of initial star masses, and thereby its radius due to the tidal effect?
Yes, absolutely. So it will, and this is a very good point. So the amount of mass lost during the collision will depend on the masses of the stars and their compactness. So it depends on the equation of state. So a more compact star will lose less mass. There's lots of numerical simulations on this. Lots of wonderful work from lots of different groups. They all show moderately consistent stories. Having said that, the amount of mass that's inferred from the kilonova observations of 1708-17, off the top of my head, it's something like 0.06 solar masses of ejecta is inferred, which is slightly higher than what most groups had predicted. So I think this is still an open question, but yes, it depends on the masses of the progenitors, their compactness as well, and the mass ratio as well.
So next one is from Prashanth, Jaikumar. What about current cryogenic detectors that are supposed to be tuned in few kilohertz range as well?
Yeah, so I don't know about these detectors. So certainly there's no, to my knowledge, there's no interferometers. Ground-based interferometers, LIGO, Virgo, Kagra, LIGO India, that are tuned to kilohertz range. If this is talking about bar detectors, which it very well may be, because certainly some of the niobium and other materials, the bar detectors have higher frequency sensitivity. But my understanding is that while their frequency range is higher and potentially in the kilohertz range, their sensitivity is a lot less, is a lot worse. So I don't think they're sensitive to these things, to these post-merger remnants. I'd love to hear if that's not right. But my understanding is that the sensitivity of those instruments is not there. There's also these much higher frequency detectors that have been proposed and built, and various things like that. Those don't get anywhere near the required sensitivity, and they're too high frequency, and there's no real astrophysical sources that we know of that can get at those. I can talk a little bit about those, but yeah. So if I'm wrong about sort of kilohertz regime, I certainly haven't heard of anything, but I'm very interested to know.
Yeah, one more from Rudrapriya Das. You talk about mainly short gamma ray burst. In this case, are not we able to see long gamma ray burst?
Yeah, absolutely. And long gamma ray bursts are something I'm very interested in as well. And when we do a lot of this magnetar work, fitting or trying to understand or explain the X-ray afterglows of gamma ray bursts in terms of magnetars, we certainly do a lot of work with long gamma ray bursts as well. And again, I'll point to all of Nikhil Sarin's various papers, which do a lot of fitting to this kind of work, to long gamma ray bursts as well. I didn't mention them at all in this talk for the one reason that I don't know how to get at the equation of state from long gamma ray bursts. So certainly we can get at how these things spin down, we can get at their ellipticity, we can get at emission mechanisms, all of this wonderful and beautiful physics. But in terms of the equation of state, for a long gamma ray burst, because it comes from a collapsing massive star, we've got no ability to understand what the progenitor mass distribution would be. And all of this work that relies on seeing on inferring the equation of state relies on understanding at least a little bit what that progenitor mass distribution is, or what the mass of your remnant neutron star would be. Whereas for the long gamma ray bursts, we have no idea of that. I'll also add those long gamma ray burst systems are a lot more messy in terms of the observations. Whereas because short gamma ray bursts, they don't emit a lot of junk around the explosion, therefore the observations are sort of a lot cleaner.
So then if you allow, Paul, I would like to take two last questions. So there are two last questions from Surendra.
Yeah,
One
sure.
is, yeah, on longer time scale, it's not only gravitational waves and B field which are key to spinning down the NS, but even bulk viscosity. Turbulence will be important. So are those effects considered while trying to fit the curves to the observed data to get the time scale of spin down? Please let me know if you think otherwise.
I do think otherwise. So viscosity and turbulence are incredibly important for understanding the dynamics of the interior of the neutron star. Once your crust freezes on the surface of your neutron star, those terms like bulk viscosity and the turbulence in the core, if it exists, and all of these kinds of things are going to affect the internal dynamics of the star, and therefore it's going to affect, whether these things glitch, all really interesting physics like that. But I wouldn't say that it should affect the overall spin down, the bulk loss of angular momentum of the star on a longer timescale. I think that is really only driven by the bulk magnetic field, so the dipolar component of the magnetic field and the gravitational wave emission. The bulk viscosity, I suppose, is going to affect whether R modes and things exist. So I guess there's something there, but we really just lump that into gravitational waves. And so, if for example, if bulk viscosity or the degree of bulk viscosity changes whether you're in the instability window for R modes, then as far as the observations are concerned, we would see that as a breaking index with n equals 7, for example. And so, you can go out and you can try and measure that. Absolutely, you can try and infer that existence. But I think it's a sort of second order effect.
Okay, so next one, the peak frequencies are good signature of hot US, but don't you think turbulence effect would change at least the quantitative picture, though not the qualitative picture?
Turbulence effects would change the quantity. Yeah, I think turbulence would be a pretty minimal role in terms of the peak frequencies. Absolutely. I don't think it'll change the peak frequency by very much at all. Those peak frequencies are really sort of given by bulk properties of the star. They're various active modes, and they're the lowest order modes. So I think turbulence, I agree, it may change quantitatively, but at a very low level that I would argue is going to be very hard to see.
Okay, so one more question forwarded from YouTube. Yanga, is it possible that NEMO detects gravitational wave from neutron star oscillations, since that sensitivity curve is lower than LIGO at kilohertz band?
Yeah, absolutely. Look, absolutely. So it's possible. Am I going to go away and bet my house on it? No. So absolutely, it's more sensitive. And in fact, I've got my slides here. Let me bring back up the sensitivity curve comparison. So the neutron star oscillations, as we heard in Deb's talk yesterday, the fundamental mode is going to be up in the kilohertz regime. And so what you can see from this plot is that fundamental mode is, we're a lot more likely to detect that in NEMO than we are with even A+, because we're a factor of, 7, 8, 9 better than A+ even, let alone LIGO, up in that kilohertz regime. So yes, neutron star oscillations, also just mountains on neutron stars. So for example, if you look at a neutron star that's rotating at anywhere from 3 to 500 hertz or 600 hertz, say, then the gravitational wave frequency is twice that high, is twice the rotational frequency. Therefore, you're talking about, anywhere from 700 to 1.4 kilohertz, give or take. So, mountains on rapidly rotating neutron stars are also something that you're more likely to see in NEMO than you are in advanced LIGO. Again, would I bet my house on it? No. And the reason is I don't know how loud F modes are from isolated neutron stars. I've done some work on this, and particularly I've done work related to, for example, how loud those neutron star F modes get rung up in a magnetar flare. And unfortunately, the answer is really poor. They don't get rung up very well at all. And there's a couple of papers that sort of go back a number of years and try to answer that. And I don't think, even a magnetar flare, which has God knows how much, 10 to the 51 ergs of energy or something along those lines, and they're in our galaxy, but the conversion to gravitational waves there is just poor. You lose many orders of magnitude getting to the gravitational wave emission. So I would love to say that, yeah, NEMO will detect these things, but I don't have a sense of how loud those signals are. Same with mountains on neutron stars. The current best limits from LIGO are 10 to the minus 6 ellipticity to 10 to the minus 8 ellipticity, depending on the type of neutron star. If you go from first principles argument and say, I've got a neutron star with a magnetic field in the core, what's the minimum magnetic field it could have, or what's the minimum ellipticity it could have? The answer is like 10 to the minus 12 or something along those lines. So there's every chance that even that signal will be too low. I hope I'm wrong on this, and I really, I would love nothing more than to see gravitational waves from an F mode oscillation or a G mode oscillation or something like that, or gravitational waves from a neutron star mountain. I hope, I work on this stuff and I'm really passionate about it, but I wouldn't bet my house on it, unfortunately.
Okay, thank you for we have taken almost all the questions, the good response from participants also. I'd like to thank you once again.